Welcome to this training module on training large language models using your own documents. Through this module, you'll learn how to train prominent language models like ChatGPT with your documents or PDFs, leveraging the capabilities of Flowise. As previously mentioned, there are various methods to train a large language model. One approach involves adjusting the model's weights through a fine-tuning mechanism. For this, a training dataset is required. Training the model with this set alerts the large language model's internal instructor. Specifically, its weights are adjusted to excel in tasks related to the training dataset. However, when our objective is for the large language model to assimilate new knowledge and employ this information to answer queries, we utilize the context section of these models. This involves feeding new data to the model as context within the prompts. Consequently, the model can draw upon this data to craft responses. A notable limitation of this approach is the token constraint inherent in large language models. We cannot feed unlimited data as inputs. Depending on the model's version, there is a maximum token threshold. For instance, GPT 3.5 tolerates around 4,000 tokens, approximately 5 pages, whereas GPT 4.0 accepts roughly 8,000 tokens, close to 10 pages. While this might seem ample, training with extensive knowledge bases or elongated documents could prove challenging. In this module, we'll delve into how Flowise addresses this restriction. So, what's the methodology for imparting knowledge to our large language model, enabling it to respond using this information? We'll elucidate this process next. Initially, we require a document containing the desired training information, in this scenario a PDF. Given that a PDF encompasses text among all the elements, data extraction focusing on the text is pivotal. A specialized component handles this. Subsequently, we employ Text Splitter, a tool designated to partition the PDF's information into distinct segments. These segments ensure we don't breach the model's token ceiling. As highlighted earlier, models interpret not text but numbers. Hence, the extracted text segments undergo pre-processing to transform them into numerical formats, specifically number arrays. An array is essentially a numeric representation of the text information. Such arrays are commonly termed embeddings. OpenAI, for example, furnishes a tool to metamorphose text segments into embeddings. Once generated, these embeddings need archiving in a vector database. These databases are optimized for handling text-derived arrays. They facilitate the construction of a semantic index, which later aids the model in pinpointing the segment containing the requisite data to address queries. Therefore, when a user poses a question to the large language model, the model consults the vector database, identifying embeddings that possess the information necessary for a response. Multiple search techniques, like similarity or semantic search, pinpoint the most pertinent text segments. A hierarchy of these segments is established, enabling the model to reference them and address the user's inquiry using the original PDF's content. Throughout this module, we'll guide you in mastering this procedure from inception to culmination, harnessing the components offered by Flowise. In this task, we will utilize Flowise to construct an assistant powered by a large language model. This assistant will be able to answer our queries using information supplied in a document. To begin, we must initiate a project within Flowise. Following this, we'll incorporate a large language model from OpenAI. To do so, we'll insert the OpenAI chat component and input our credentials. For our purposes, we'll employ the OpenAI large language model known as GPT 3.5 Turbo. Next, we must integrate the conversational Q&A chain. We'll navigate to the chain section and opt for the retrieval Q&A chain component. This feature facilitates answering questions rooted in document-based information. Within this interface, we notice that it mandates two components, a large language model and a vector story. We'll then connect the large language model we have previously set up. Our subsequent step involves setting up the vector story, which will house snippets from a PDF document. Exploring the components further, we'll locate the vector story section. Various vector databases are available. For our preliminary testing, we'll select the local memory option. However, For deploying this project in a real-world scenario, it would be prudent to lean towards advanced vector databases, such as those offered by Pinecone. After adding this component, we observed two entries labeled Document and Embeddings. In the context of the document section, we are addressing not PDFs directly, but rather documents enriched with metadata from utilities like LangChain. Thus, our PDF will enter a pre-processing stage where the content gets fragmented. Subsequently, with the assistance of an embeddings component, an array will materialize. Initially, we'll associate the in-memory vector story with the retrieval chain. After that, we'll need a document loader to segment the PDF. Our initial move will be to incorporate the document loader, which can be found under document loaders. Multiple options are visible for Excel, CSV, or JSON files. Given our needs, we'll pick the one designated for PDFs, labeled as PDF file. Given our needs, we'll pick the one designated for PDFs, labeled as PDF file. After its integration, it will be connected to the vector story, ensuring its documents are sourced from the PDF loader. We then proceed to upload the PDF. For this example, we'll upload an article about GPT-4o from 2023, a tool unfamiliar to the language model. We'll select the appropriate file, click Upload, and then opt for the relevant PDF, culminating in the document's successful upload. By following these steps, we have achieved a significant portion of the project. We have enabled access to OpenAI's large language model, established the Q&A chain for querying based on the vector story data, and uploaded the essential PDF. In our forthcoming task, we'll delve into the addition of a PDF fragmenter, ensuring we remain within the OpenAI model's token constraints. We'll also explore the deployment of the OpenAI converter, which is crucial for generating the indispensable embeddings that allow the model to function optimally. In this task, we will finalize the programming of our conversational assistant project that draws on information from our PDFs to answer questions. In the preceding task, we integrated a large language model, specifically the OpenAI retrieval query chain. This enhancement enables the assistant to respond using data stored in a vector database. Moreover, we incorporated the in-memory vector stored to house the embeddings and developed a mechanism to process and extract text from the PDFs. One remaining component essential for our project is the PDF splitter. It ensures we don't surpass the token limit when generating embeddings. Let's kick things off with this splitter. For its implementation, we need a text splitting tool. Upon navigating to the components and exploring the text splitter options, we encounter multiple choices. We'll opt for the recursive character text splitter. This needs to be connected to the PDF file and the fragment size determined. Options include 1000, 2000, or 5000 tokens. However, to remain within the GPT 3.5 token constraints, we'll choose a limit of, say, 500 tokens. Additionally, there is the chunk overlap feature, dictating the number of tokens shared between adjacent fragments. Maintaining an overlap is pivotal to ensure no vital information is shared across fragments. Following the integration of the text splitter, the embedding component is next in line. In its designated section, we observe various available tools. Azure boasts its primary system, as does Hugging Face, which provides pre-trained large language models. Nonetheless, we'll select OpenAI Embeddings and Embedding Processor from OpenAI. During its integration, it will prompt us for credentials, which were previously established. Once linked, the vector store offers an option to set the top K. By default, this is at 4, meaning during data searches, the top 4 most relevant fragments are retrieved. We can increase this to 8 if we aim to source information from a more extensive fragment set. With all configurations in place, we proceed to the testing phase. Post saving our settings, we can pose questions related to the uploaded PDF. If we, for example, inquire about GPT-4o, the assistant should reference to the PDF to furnish an answer. This feature proves invaluable, especially since GPT-4o was conceived in 2023, a fact not inherently known to the GPT 3.5 model from OpenAI. For a deeper dive, like questioning the GPU costs associated with model training, the assistant should provide an accurate response, highlighting its reliance on our document. This system's brilliance lies in its ability to educate any large language models with diverse information. This facilitates customizations with content from PDFs, TXT files, Excel sheets, and even unstructured formats like JSON. As a result, we can craft highly specialized models that tackle a myriad of questions anchored by our tailored data repository.